So dear students, welcome to today's lectures, and we have reached sections 4.6.1 and 4.6.2, in which we generalize the stochastic calculus we've been looking at so far, and we generalize it towards multiple dimensions. So we will be dealing with multivariate stochastic calculus in this section. The setting. So we start with a definition, the definition of a d-dimensional Brownian motion, where d is larger or equal to 2. Two-dimensional Brownian motion, three-dimensional, up to multiple dimensions. And that is a process, in fact, that we write as follows. It is wt. It's a vector-valued function consisting of w1t, w2t, up to wdt. And the definition is as follows. It has the following properties. Each individual wit, t greater or equal to 0, that is a one-dimensional Brownian motion for all I, 1, 2, 3, up to d. That is the first part of the definition or of the properties. And the second part is when I is not equal to j, then wit, t greater or equal to 0, is independent of wjt, t greater or equal to 0. So when I is not equal to j, then these two are independent. Well, another part of the setting is the filtration. Of course, we need a filtration for the d-dimensional Brownian motion, and that filtration satisfies the following properties. First of all, it is denoted again by script f. The filtration fs is contained in ft when time s is less or equal to time t. And that is again our notion of accumulating information. Information accumulates, and we often write that by this notion, so that the filtration at time s is contained in the filtration at time t. Secondly, we have the measurability. Wit is ft measurable for all d components, and that is denoted as the adaptivity. We know that from the one-dimensional case by adaptivity. And the third one is the independent increments. We have also seen that in the one-dimensional case, and in the multidimensional case, this generalizes as follows. When 0 is less or equal to t is less or equal to u, then the increment, the vector valued increment wu minus wt, and that with that we mean w1u minus w1t, w2u minus w2t, up to wdu minus wdt, that is independent of ft. And each of these individual components are then independent of ft. And we know that by the notion of independence of future increments. Now, if you remember, the differential notation was very convenient. And from this, we can write, from this definition, we can write in terms of the differential notation, wit is dt. Think of the first property that says it is a one-dimensional Brownian motion, and that immediately implies that w1t, wit is dt. That is the quadratic variation. And we have the cross variation here, wit, wjt is equal to 0 when I is not equal to j. You can extract that from the independence property that we have just mentioned, but we can also prove it. So we will show a short proof here below. And the claim in that proof is that the cross variation wi, wjt is equal to 0 when I is not equal to j. And how do we show that? Well, remember, in the one-dimensional case, we come up with a partition of time interval. We partition it in time slices, I plus 1, j plus 1, etc. And we write down the definition the cross variation Wi, Wj in those intervals. So we have a partition and we have the intervals. We write it down as a sum. A sum k is equal to 0 to runs from 0 to n minus 1 of this cross variation Wi tk plus 1 minus Wi tk times Wj tk plus 1 minus Wj tk. That is the cross variation over the time partition, the sum. And then we take the limit in L2. So the limit of the partition, the maximum size in the partition going to 0. And the limit in L2 goes to 0 then. That is basically the claim that we make here. Yeah, that the cross variation taking the limit in L2 is equal to 0. And what do we mean with that? Well, what we mean with that is this sum here. This sum here we denote by CPN, and C stands for correlation. CPN, the sum k runs from 0 to n minus 1, Wi tk plus 1 minus Wi tk times Wj tk plus 1 minus Wj tk. And then what we mean by this taking the limit in L2 going to 0, that is that we need to show that in limit the mesh width going to 0, in expectation Cp square, Cpn square is equal to 0. So we need to square the expression, take the limit and show that it goes to 0. And there we will see many of the derivations that we have done in earlier lectures. So let's write down Cpn square, and that is the sum k runs from 0 to n minus 1 of this part square, Wi tk plus 1 minus Wi tk square times the other one, Wj tk plus 1 minus Wj tk square plus the cross term. So let's look back. We see this one times this one, and we can write the square of taking the square of this. We can write it as follows. It is the square of these two plus 2 times the sum. K runs from 0 to n minus 1. It's a double sum, the sum L greater than K of Wi tk plus 1 minus Wi tk times Wj tl plus 1 minus Wj tl. So we have written out the expression c squared this way, and now we need to take expectations. Well, what a good news is, of course, that increments are independent, as we have shown in the properties, independent increments. So taking the expected value is the expectation of this multiplication is the multiplication of the individual expectations. So we can write that down. Taking the expectation of c square is then the expectation of this first term, expected value of, and of course we can take the sum out because of the linearity of the expectations. Expectation of Wi tk plus 1 minus Wi tk squared times the expected value of Wj tk plus 1 minus Wj tk squared plus taking the expectation in this mixed term. And in this mixed term, we see only I not equal to j appearing. And these expectations are all 0. So the part that comes from this cross term, we don't write down because it's equal to 0. Now, if we look at these expectations, we see here quadratic variation, square increments, sorry, we see square increments of Brownian motion, and they are connected to the variance. So this one here is tk plus 1 minus tk. And the expected value here is the same, tk plus 1 minus tk. So taking them together, it's the sum k runs from 0 to n minus 1, tk plus 1 minus tk squared. And we remember that is dt squared, and we have shown that that goes to 0 when the partition size of the interval in the partition goes to 0. So that is the proof of this notion here, proof of the claim that the cross variation wi, wj is equal to 0 when I is not equal to j. We will move on, and we will move on to the 2D case. We will consider the two-dimensional case in more detail. Well, in the two-dimensional case, Wt is given by W1t, W2t. It's a two-dimensional Brownian motion with the filtration script ft, t greater equal to 0. Now here we can define an Ito process xt, t greater equal to 0 with respect to the two-dimensional Brownian motion. That is a process satisfying the following: xt is equal to x0 plus the integral from 0 to t theta u du plus the integral from 0 to t sigma 1u dw 1u plus the integral from 0 to t sigma 2u dw 2u. And we can write that in differential form. Of course, that is always the more convenient form to work with. And we would write that as dxt is equal to theta t dt plus sigma 1t dw 1t plus sigma 2t dw 2t. And here we see three functions appearing: theta t, sigma 1t, sigma 2t, and they are adapted to the filtration ft, t greater equal to 0, and we assume that these three functions satisfy all the needed conditions for the integrals to exist. So this is the definition of the Ito process in the two-dimensional case. Now suppose we have two of such Ito processes, x and y. How does it look then? So let's again immediately consider the differential notation, the differential form. It's most convenient. So in that case, we have dxt is equal to theta 1t dt plus sigma 1t dw 1t plus sigma 2t dw 2t. And for y, the dynamics for y, dyt is equal to theta 2t dt plus sigma 1t dw 1t plus sigma 2t dw 2t. So writing this in vector notation, you see here something like a drift vector, theta 1, theta 2, and here in fact we see a matrix appearing. So we can write this even as in a matrix form. Dxt is equal to theta t dt plus a matrix sigma times dwt. And then here we have a matrix consisting of sigma 1, t, sigma 2, t, sigma 1, 2, t, and sigma 2, t. So the generalization to two such processes gives us vector valued systems with xy here, theta 1, theta 2 here as a vector, and here we even see a matrix appearing, and matrix with volatilities, sigma 1, sigma 1, 2, sigma 2, 1, and sigma 2, 2. Now we can look at dx dx, the quadratic variation, dx dx. We can just multiply dx with itself in the computational rules that we have learned. Well, the first one with itself will give a dt squared term that will cancel out. dt dw1 will cancel out. dt dw2 will cancel out. dw1 with itself will remain. dw2 multiplied by itself will remain. Those are dt terms. as you recall. And the mixed term here, that will again be 0 because these two, W1 and W2t, are independent. So if we do that now by heart. You can write it out if you need it, but we can see that this, in fact, this dxt is sigma 1 squared t plus sigma 1 2 squared t times dt. And the same for dy. We can do the same for dy. And for dy, we get essentially the same. dw1 will give us a dt. dw2 will give us a dt. The mixed term will cancel out. And higher orders, dw1 dt, dw2 dt, the cross variations will be equal to 0. And dt squared will also be equal to 0, resulting in sigma 2 1 squared t plus sigma 2 2 squared t dt. And we can also look at the cross variation. Here, dxt dyt, we multiply the first one with the second one in our computational rules. The first one multiplied by the second one. And we see dt terms that will disappear, cross terms that will disappear. We see these terms, the multiplication gives us a dt. So it will be sigma 1 1 t, sigma 2 1 t dt, plus here sigma 1 2 t times sigma 2 2 t dt. And we can take the dt out and get sigma 1 1 t times sigma 2 1 t plus sigma 1 2 t times sigma 2 2 t dt. And that is, of course, the cross variation, an indication for the cross variation. So with two of such Ito processes, we have a vector valued form. We can say something about the quadratic variations, and we can say something about the cross variation. Now, how is the two-dimensional Ito-Dublin formula? Again, that is a straightforward generalization of the one-dimensional case. It's written down in the book as theorem 4.6.2. And let's go over it in some more detail. Let again W be Wt, and that is a two-dimensional Brownian motion, W1t, W2t, t greater equal to 0. A two-dimensional Brownian motion with a filtration script ft, t greater equal to 0. And let's have the two Ito processes xt, t greater equal to 0, and yt, t greater equal to 0. These are the two Ito processes, and formally they are written in integral form as follows. Xt is equal to x0 plus the integral from 0 to t theta 1 u du plus the integral from 0 to t sigma 1 1 u dw1 u plus the integral from 0 to t sigma 2 1 u dw2 u. And for y, we have it similarly defined. Yt is equal to y0 plus the integral from 0 to t theta 2 u du plus the integral from 0 to t sigma 2 1 u dw1 u plus the integral from 0 to t sigma 2 2 u dw2 u with respect to our wt. And this looks, of course, again in differential form, it looks like this, right? Now, the two-dimensional Ito-Dublin's formula, this is the basis, and then it goes as follows. We have a function, f, and f depends on t, x, and y in this case. It's a multi-dimensional Ito formula in 2D here and in multi-D. There may be other variables here. It could be an x1, x2, x3 if you go to higher dimensions. But now here, suppose we have f depending on t, x, and y. And suppose this is a function with continuous first and second derivatives. Then in that case, we look again for the df, f depending on t, x, t, y, t. And then the generalization is as we would expect it to be. It is a little similar to the multidimensional Taylor expansion. It's df dt, plus df dx times dx plus df dy times dy. And then we get the second derivatives plus 1/2 the second derivative of f with respect to x dx dx plus 1/2 the second derivative with respect to y dy dy plus 2 times the mixed term. So 2 times 1/2 makes 1, so plus the mixed derivative df dx, the second derivative of f with respect to x and y, times dx dy. That is the multidimensional or the two-dimensional Ito-Dublin formula. Again, a straightforward generalization. It is a generalization as we would expect it. Now we have a corollary. So, and that is the Ito product rule that follows immediately from this two-dimensional Ito-Dublin's formula. And that is as follows. Suppose xt and yt are given as above, then the corollary says the change d xt yt is equal to yt dxt plus xt dyt plus dxt dyt. And this last part is a new part. That is again the part that comes from the stochastic calculus. The first part is the classical part, the part of the product rule, y dx plus x dy, but we have another part here, dxt dyt, and that can easily be seen from the two-dimensional Ito-Dublin's formula. So that part, that last part, is due to the cross variation or due to the correlation. Yeah, and we can prove that corollary easily by making use of the two-dimensional Ito-Dublin formula, and for that then we would take our f t x y being x times y. So there's no time dependency, and therefore the first derivative with respect to time is equal to 0 in this case. The first derivative with respect to x d dx of x times y is equal to y. The first derivative with respect to y is equal to x, and all the second derivatives are equal to 0. Yeah, and not all, but the second derivative with respect to x, the second derivative with respect to y are equal to 0, and the mixed derivative is equal to 1. And that mixed derivative gives us this part. So if we substitute these findings, these derivatives in the two-dimensional Ito-Dublin formula, immediately we find this Ito product rule. So that makes the proof of the Ito product rule. Well, this concludes the first lecture for today. And because the next part will be dealing with a slightly different topic, we will stop here, have a break, and then continue.